Welcome everyone. In this session, we are going to explore principal component analysis, commonly known as PCA. PCA is one of the most widely used techniques for simplifying complex datasets, especially when dealing with high dimensional data. We will cover what PCA is, why it's useful, how it works, and look at some real-world applications. Principal component analysis is essentially a mathematical tool that helps us make sense of complex data. In big data sets, variables can overlap or carry redundant information. PCA reduces the number of variables but tries to return the most critical information. It does this by creating new variables called principal components. These components capture the underlying structure of the data more efficiently, making it easier to analyze, visualize, and work with. There are several strong reasons to use PCA. First, it simplifies data without losing too much information, which is especially helpful in fields like engineering, finance, and genetics. Second, it allows us to visualize very high-dimensional datasets by projecting them into 2D or 3D. PCA also handles multicollinearity. When variables are correlated, they can confuse many models, but PCA solves this by creating new uncorrelated components. Lastly, reducing the number of features speeds up machine learning algorithms. To understand PCA deeply, we need to grasp three key ideas. Variance is the first. PCA seeks directions where data varies the most because variance means information. Principal components are new variables created as linear combinations of the original ones. Think of them as axes rotated to better fit the data. Orthogonality is also crucial. Principal components are perpendicular to each other, meaning they are completely uncorrelated. This ensures that each component adds unique information. Here is a step-by-step of how PCA actually works. First, we standardize the data to remove biases caused by different units or scales. Next, we calculate the covariance matrix to see how features vary with each other. Then we compute the eigenvectors and eigenvalues of that matrix, which gives us the principal components and how much variance they capture. We sort the components by their eigenvalues and choose the top ones. Finally, we project our original data onto these new principal components, resulting in a simpler but meaningful dataset. Let's now build a strong intuition for what PCA actually does by looking at these graphs. The first graph is the original data with principal components. Here we see a scatter plot of data points spread out unevenly. Notice how the data is stretched actually in one direction, then another. It's not aligned with the original X or Y axis. PCA identifies the direction where the spread or variance is the largest. This direction is marked by the first principal component, shown as a long arrow. The second principal component is perpendicular to PC1 and captures the next most variation. PC1 principal component 1 and PC2 principal component 2 are our new axes, and they better fit the true shape and structure of the data compared to the original axis. In the second plot, we see the result of projecting data onto the first principal component. Instead of dealing with 2D data, we have compressed it into just 1D, values along PC1. This projection captures most of the original data's variability while reducing the dimensionality. You can think of it like shining a flashlight along PC1 and catching the shadow, the most informative shadow that still preserves the shape of the original cloud. A few important properties to remember. The first principal component always captures the maximum possible variance. Each subsequent component captures the maximum remaining variance but must be orthogonal to the previous ones. Also, PCA is highly sensitive to the scale of the data. That's why standardization before applying PCA is absolutely necessary. If variables have very different scales, PCA might get biased toward larger scale features. Not every principal component is equally useful. To pick the right ones, first check the explained variance. Components with high eigenvalues are better. Next, use a scree plot where we look for the elbow, the point after which adding more components offers little extra value. Another approach is to look at cumulative explained variance and keep enough components to reach 90 to 95% of the total variance. Finally, use your domain knowledge. Sometimes components that capture important real-world features must be kept, even if they explain less variance statistically. This visual shows two important tools. On the left, the scree plot shows a sharp drop-off after the second component. That's the elbow, suggesting we should keep only the first two. On the right, the cumulative variance plot shows how many components are needed to explain a certain percentage of the total variance. Typically, we want to capture at least 90% to ensure our model remains accurate but simpler. In engineering systems like bridges, airplanes, or factory machines, sensors continuously collect massive amounts of data, including vibrations, stresses, and strains. PCA helps engineers by analyzing this data and identifying what normal patterns look like. When new data deviates from these patterns, PCA can quickly detect early signs of damage or faults. This allows for early maintenance or repairs, preventing costly failures. Essentially, PCA acts like an early warning system, flagging issues before they become serious. In face recognition, images are typically made up of thousands of pixels, which results in very high-dimensional data. Processing every pixel individually would be extremely slow and inefficient. PCA comes to the rescue by reducing the dimensionality. It extracts key features known as eigenfaces, which are essentially the principal components that capture most of the variation in human faces. by projecting face images onto these eigenfaces, PCA makes face recognition much faster and is still very accurate even with much less data. Financial datasets are often complex and noisy, involving thousands of variables like stocks, bonds, commodities, and currencies. Many of these financial variables are highly correlated. PCA simplifies the problem by finding new components that summarize the market's main trends. Instead of analyzing each stock individually, analysts can focus on just a few principal components that capture most of the market behavior. This not only makes the analysis easier, but also improves risk management and portfolio optimization because it highlights hidden relationships among financial assets. In bioinformatics and genetics, datasets often contain measurements for thousands of genes across a small number of samples. Analyzing this kind of high-dimensional data directly is difficult and inefficient. PCA helps by finding patterns in gene expression that separate groups such as healthy individuals versus those with cancer. It reduces the data to a few principal components that highlight biological differences. This simplification not only speeds up analysis, but also helps researchers and doctors discover hidden patterns in the data, enabling early disease detection and personalized treatment strategies. In environmental monitoring, large networks of sensors collect data on temperature, humidity, air quality, and pollution levels. However, this data is often noisy and redundant. PCA helps by filtering out the noise and reducing the size of the data without losing important information. This compression is especially valuable for Internet of Things devices where battery life and transmission bandwidth are limited. By using PCA, smart city systems and agricultural monitoring setups can process environmental data faster and more efficiently, enabling real-time decision-making and more sustainable sensor operations. To wrap up, PCA is a highly effective tool to manage high-dimensional data. It simplifies datasets by finding new uncorrelated variables, principal components, that explain most of the variability. PCA is extremely useful for visualization, noise reduction, and preparing datasets for machine learning models. By reducing the number of features, it not only speeds up computation but also helps models generalize better to unseen data. It's a must-know technique for anyone working with large and complex datasets. Note: PCA is powerful, but it has limits. It's a linear method, so it misses curved or manifold structure. Because it is unsupervised, it maximizes overall variance rather than what matters for your target, which means it can discard low variance signals that are actually predictive. Results are scale sensitive. Variables with larger unit dominate unless you standardize. And PCA is outlier sensitive. There, a few extreme points can rotate components dramatically. Interpretation is often tricky because each PC is an opaque mix of features and its global focus can distort local neighborhoods or blur cluster separation. Finally, PCs can drift over time as the covariance structure changes, and there are practical pitfalls. You must impute missing values first and avoid data leakage by fitting PCA only on training split. To mitigate these issues, standardize features and check outliers before PCA. If prediction matters, consider supervised dimensionality reduction like PLS, LDA, or nonlinear options like Kernel PCA. And fit PCA after the train test split in pipeline with cross-validation. Monitor drift and refit as needed, and use loadings or sparse PCA to improve interpretability.